Welcome everyone. Today's speaker is our own Zack, who joined the CITA last October. And yesterday I asked Zack to send me some brief bio bullet points to use for introduction, and he kindly sent me some. In college, he wrote an essay about the existence of aliens, which was already $25,000. So is this US dollar or Canadian dollar? US.
It's a real story.
Okay, US.
There was a contest, and I wrote an essay about how I thought aliens are totally out there.
Right. So did you spend this money, or when are you going to spend it?
I was on a lot of need-based financial aid, so they just deducted that my financial aid. So I actually received no money for the essay.
Okay.
I met JJ.
Yeah, sure. So and it continues. So event where he received the award, he met his future CITA office mate JJ. So unfortunately I don't see JJ here, but I was gonna ask him the same question, whether he got the same $25,000. So there's a total of potentially $50,000 in the room 1404. So you can knock the door. So we have to think about writing an essay rather than a paper. And then it continues. So he did his PhD at Princeton, where he successfully changed the policy so that coffee would be free for astronomy graduate students. Previously, you had to pay per drink. So, oh my goodness, so you got this $25,000, but you didn't want to spend time on
That's right.
That's right. So that shows who you are.
Yeah. Yeah, very miserly.
And then it continues. So in his spare time, he has recently studied woodworking in a makerspace in Chinatown. Though he has made some small furniture items, he has an ultimate goal. He is tired of certain parts of cooking and plan to automate aspects of the pipeline. Maybe you can hire a cooker chef for using the 50.
I built my own.
Right. Yeah. So and this is it. So he sent nothing about his research or academic career. So let's hear directly from him about his research. Zack, please take it away.
Yeah, thank you. I'm Zack. I'm a postdoc at CITA. I got here in the fall. And I work on mostly the CMB, a little bit of large scale structure. And I'm interested in cosmology, what is the universe doing at the large scales? And so in this talk, I'll discuss both data and theory. And I'll start with data. So this is what I'm really passionate about. I think cosmology historically has been a field that's been led by data because the universe is surprising. It's not in a steady state, right? A Big Bang happened. It's flat. Why is it flat? So the best way to figure out these things is to go out and look at the universe, measure parts of it. So there's Penzias and Wilson with their sweet feed horn antenna. And the CMB is just has been a gift. So I'm going to do a sort of lightning historical review. But this gap between the CMB and the foregrounds is incredible. It lets us isolate physics from astrophysics in a way that's very hard to achieve with other methods. CMB is super bright relative to pretty much everything else in the gigahertz band. And this is in temperature. It's even better in polarization. And this is a beautiful figure from Kobe. So the CMB is this nice black body from the surface of last scattering. And you see just how well that spectrum looks like a black body. Another part I like about this figure is this sort of breathless, excited statement. Theory and observation agree. And so it wasn't like that back in the Kobe days. But this statement has really echoed through the decades. It's maybe a blessing and a curse because it has held true. So the CMB, it also has anisotropies, and this is what gives it a lot of the cosmological power. And over time, we've gotten better and better at measuring them. So this is from around the turn of the century, 2000, and you have this crazy plot. All these people are trying to measure the the first few peaks of the CMB, just trying to nail down what exactly the contents of the universe is. Just a decade later, you have WMAP and then a Boomerang really nailing the first few peaks. By now, we know that the universe is flat, that it seems to have some dark matter component that draws the matter in gravitationally. And then we get to the Planck era. Now we have a cosmic variance limited measurement of the temperature power spectrum. So temperature is done. And the constraining power comes, so here's a plot from the Dodelson's textbook, which is great, showing that this power spectrum is so sensitive to really just fundamental aspects of the universe. So this is the curvature of the universe. Do we live in a flat or closed or open one? And the locations of the peaks shift based on that in a very sensitive way. And similarly, the universe we think is filled with cold dark matter. And that has profound effects on the CMB because that's really the potential wells that the photons and baryons are sloshing around in. And so, we built this standard model now, and the CMB is this critical building block. We now think we live in this cold dark matter and dark energy universe. So, I just showed a bunch of CMB getting better measurements. There's also improvements in supernova, for example. And so, with the improving measurements, we also begin to see hints of tension. And so I think this is one of the big conversations happening in cosmology right now, is this Hubble tension. Just how old is the universe? It's a very simple question. It's amazing that we can answer it in different ways. But the different ways seem to yield different answers. So we built this model. We have a pretty good idea of the different components of the universe. It's pretty much all dark though. Like we don't know what dark energy is. We don't know what dark matter is. And I think also neutrino physics is sort of an open field. Black holes also very mysterious. So much of the universe still remains to be discovered. And so, I think really the best way to make discoveries is to take new data. So here is Vera Rubin taking some new data in order to better understand the universe. This is at Lowell Observatory. So we, in the CMB field, I think, are moving towards ground-based observatories in order to really measure the small scales. And so these happen mostly at two sites right now, the South Pole and the Atacama Desert. This is a picture of the Atacama with a bunch of different cosmology instruments. And so this is sort of the regime where the action's happening at the small scales, at least. So above is temperature. So we finished with that with Planck. We built this nice satellite. We measured cosmic variance to multipoles of around 2,000, maybe 2,500. But the polarization, which is this middle plot, there's still much to discover. The temperature and polarization cross correlation is also a great data set. That's just at the small scales, which we target from the ground. There's lots of great instruments that are doing this. So ACT is an instrument that I've long been a part of. SPT is observing at the South Pole. They target very small scales. And then upcoming, we have the Simons Observatory, which I'll talk more about. And then at the end of the decade, we'll have the CMB stage 4, which has been positively described as the decadal. And so what we're going for is just more precise measurements between Planck and ACT, which is a sort of a current stage 3 instrument. We have a factor of 3 lower noise. And then we'll get another factor of 3 lower with the Simons Observatory. And the timeline is very fast. We're expecting SO to have first light next year. I do want to mention that there's also this frontier of the large-scale polarization. So the cosmic microwave background is also a great way to probe inflation, and primordial B modes are a window into that. So a bunch of different instruments are targeting that. Just mentioned, Bicep Keck and Simon's array in class are all looking at this sort of large-scale polarization sky right now. Balloons are a great way also to look at the large-scale polarization. And then LightBird is this joint JAXA and European mission that is planned to be launched in 2028. So I'll talk about now the Simons Observatory. This is a project I'm really excited about. It's happening right now. And the Large Aperture Telescope is the one I'm most involved with. It's a big 6-meter telescope, and it'll measure the CMB in 6 bands, from 30 to 280 gigahertz. And it'll have 30,000 transition edge sensors. So for context, Planck had 52 sensors, or detectors rather. So we're making the sort of a Moore's law type improvements in terms of sensitivity. ESO will also have a bunch of these little telescopes. It turns out that to measure the large scales, it's nice to build a small telescope where you can keep everything cold and everything stable. And so these small aperture telescopes, the instruments in the middle, and then there's sort of a ground shield around it. Many of these will be built possibly in different locations, and then at least for S4. So for SO, I think they'll all be in the Atacama. Those will target gravitational waves. And we hope to survey, half the sky with increasing precision, just much lower noise. And in particular, also a much tighter beam. So we'll be able to target small scales. So Planck had a sort of a low resolution compared to these ground-based observatories. And this site is going to really be populated with different telescopes. Right now, there's already plenty of action happening in the Atacama, and SO will be right there with them. The reason also why we choose the Atacama is that it is there are problems with doing CMB work from the ground. Moisture is, I guess, the big enemy. Water vapor in the atmosphere just causes a ton of large-scale noise in your detector, and so the Atacama is a great site for that because it's very dry. So we have exciting science goals for SO. This is just a big table of them from the science paper. I just want to point out this this little sub table here related to the light relics. So these are the number of relativistic species in the early universe. So corresponding to things like neutrinos, which is what the CMB is sensitive to, and also the mass of the sum of the neutrino species. So what instrument is going to get you a factor of 4 improvement in the number of neutrino species for less than 1 billion, right? This is a deal in terms of particle physics. And it's also amazing that we can do particle physics using the early universe. And this is all happening right now in the present. So this year, we're going through validation, integration, and testing of these instruments. We expect full science, the first science observations to happen next year for the Simons Observatory, and then half a decade of science. So one of my roles in this vast machine that goes towards building the standard model is power spectra and covariances. So much of my thesis was to work on preparing for this observatory by getting ready to combine the Planck data, which observes these kind of large-scale temperature fluctuations, with these small-scale polarization measurements we're going to get from the ground. And so to do this correctly, so that the spectra we get out from these telescopes is correct, requires various details. So here's a paper I wrote 2 years ago about reproducing all the Planck analysis with an eye towards the Simons Observatory. So this is all Planck data that we put through the SO pipeline. Also, I just want to point out, this is a crazy plot. All of these spectra are different frequencies. These are different combinations of temperature and polarization. And this line that we've drawn through all these data points is right in the middle of them. That's remarkable that the theory and observations agree. It's not guaranteed that the polarization spectra in particular would agree so well with the temperature at all scales that we've measured so far. It says, I think, important things about the nature of, for example, dark matter, that it seems to have had some effect in the early universe. So, just to summarize, CMB cosmology in the next decade, we're ever more precise, ever larger instruments, especially with small scale polarization and lensing. I don't work on the large scale polarization stuff, but there's also a lot of exciting things happening there in terms of the inflation front. And then there's exciting science to be done from secondaries like SD or clusters, perhaps. Okay, so all this great data is going to come in. We want to also combine it with things like large-scale structure data. So, for example, galaxy surveys. And so this is something that is sort of a CITA specialty. So correlated simulations are required of the CMB sky. So Web Sky sort of had its start in the CITA, where you make simulations of the microwave sky, for example, with SD or with the CIB or with lensing. And you need these simulations in order to create analysis pipelines, so that in a couple of years, you can robustly combine galaxy data with CMB data and get out your standard model of cosmology, or something different maybe. So I'm taking these slides from Jia Liu because they are just very nicely illustrated. The reason why we need these simulations is because as you have one CMB photon leave the surface of last scattering and reach us, it goes through this whole universe of intervening material. So for example, the kinetic SD and the thermal SD involves this one photon interacting with electrons in the universe. The ISW, or the integrated Sachs-Wolf, involves this photon interacting with evolving gravity. And then CMB lensing, right? So there's matter in the universe. And so this photon is going to feel the effects of clusters or halos, dark matter. There's also this cosmic infrared background, which is this whole cosmological record of emission from dust, from star formation. And radio galaxies. So I'm really into these, but they're basically every AGN in the universe you're going to end up seeing in your CMB map because they're so bright. So I just want to advertise sort of an effort towards this. We're putting together sort of a successor to Web Sky, which we're calling Half Dome, both after the nice mountain, but also because we're only going to simulate, I think, half or maybe even a quarter of the sky. And this simulation set is going to be targeted at next generation surveys. So we're going to try to basically make a simulation set that works for every single one of these galaxy or CMB surveys to enable joint analysis. So we're going to go to Lmax of 5,000, so it's a multipole, so the resolution in terms of angular scale, and try to go for relatively low masses of 10 to the 12 solar masses. And we'll make maps of all these different foreground components. And this, I mean, it's important because we want to do joint analysis of all these really interesting instruments that are going to happen in the next decade or more. So for example, DESI has recently been observing. We have the Rubin starting up soon. And then also various other galaxy surveys. And that data needs to be combined with the CMB surveys. So for example, Simon's Observatory, I said, starts taking data next year. And then later we'll have Lightbird and S4. The need for these sims, I think, is great. So in terms of this effort, I'm leading the kind of CMB modeling aspect. So these different gigahertz range foreground components, we hope to make models of these that are updated to, based on new data, and then generate simulations of the sky based on them. And these will be Halo models for now. And so this is the whole team, lots of people, and we hope to be running these simulations on DOE computers, probably NERSC. So there's a lot of challenges here, which is why people haven't done it yet. How many simulations do we need of the full sky? Well, for a finished set of Galaxy and CMB surveys, we probably want 1,000, right? We want to characterize things like covariance. That's a lot of computing time. We need 500 million CPU hours, roughly. And it's also not easy to coordinate storage. These are huge simulations. So something that WebSky has encountered certainly is that keeping all this dark matter on disk is not easy. And then who's going to pay for it? So if you want to do cross-instrument science, it's not obvious who's going to fund the big simulation set that you need to do that. So we hope to surmount all these challenges and make one nice set of dark matter simulations. And we hope it'll provide sort of a baseline for these next generation surveys. So obviously the universe is not just dark matter. There's a lot of baryons, there's a lot of galaxy formation and other crazy stuff happening. But with this set of n-body sims, we'll do WebSky-like Halo modeling on them to generate mocks of the gigahertz sky, for example, and also just optical galaxies. But on top of that, we can also try different strategies of mapping hydrodynamical simulations to this big set of n-body sims, and do things like train emulators or surrogate models. And something I'm really excited about is that the data and the theory here goes both ways. The data, for example, from the Simons Observatory, it's going to tell us a lot about what these galaxies are doing. So even in ACT, we see these radio galaxies everywhere. They're very bright, especially at lower frequency. And the SO catalogs at the end of the day are going to have tens of thousands of these sources. And that's going to let us nail down the models for things like the CIB. Okay. So that's a lot of exciting stuff that's going to happen towards building this standard model of cosmology. I will now tell a story. So I said this earlier in the talk, and the best way to make discoveries about the universe is to go and look at it, try to see aspects of it. But we are at CITA, we're at a theory institute. Where does that come in? So we're going to go back in time just a little bit, very small fraction of the Hubble time, to the Ming Dynasty. It's around the year 1400 in Europe, early Renaissance, I think. And the hero of our story is named Wang Yangming. We're just going to call him Wang. And he's, 20-something. He just got his degree. He's ready to apply what he's learned to the world. He's ready to start his postdoc. And around this time, in the Ming Dynasty, the great thinkers, the CITA faculty of this era, if you will, they are really on board with this statement. They are on a rationalist kick, and they even have a pithy saying that translates to basically this: that if you want to learn things about stuff, you have to go inquire about it. So these are Neo-Confucians, and our hero Wang, he's a huge fan of the Neo-Confucians. He's grown up reading all their books, and so now he's ready to start his career, and he thinks, "Wow, time to observe, time to apply what I've learned. Time to observe the universe." So he goes to his garden, and he sees a grove of bamboo, and he thinks, what a great opportunity, time to observe the universe. So he looks very intently at this grove of bamboo. A day passes, another day, another day. He's doing nothing but looking at this grove of bamboo. 6 days pass. He's done nothing but look at this bamboo, just sitting in his garden. After 7 days, he gets really sick because he's done basically nothing except look at this grove of bamboo. And he thinks to himself, I've learned nothing about the universe. This whole Neo-Confucian stuff is useless. Like what? This is terrible. I've observed for so long, yet I've learned nothing. So actually, our hero takes this lesson to heart. He becomes one of the most influential thinkers of his time, based on this idea that it's not enough just to take data, right? That you need a reason. You need your mind, like understanding comes from you, right? It's not enough just to have some data, whether it's data from a telescope or data in a simulation, right? That's not understanding. So that's the role of theory. I'm so excited about all these big CMB surveys that are going to come out, but here at CITA, like we give reason to that. Okay, so sorry about that brief historical interlude, but I read that story recently and it just really stuck with me. Okay, so now I'll talk about my theory efforts, especially differentiable theory. And this is for both CMB and large scale structure. So I've been working on this code. It's called Bolt, and it's a Boltzmann code. So this is like CAM or class. It takes parameters and it evolves, using linear perturbation theory, very standard stuff, to get observables for the CMB, for example. And so the physics here is very well settled. Like Bond and Evstathiou is like one of the great papers on this, for example. So here's a figure from Baumann. Basically, in the linear theory, you have only certain interactions that are happening. Everything touches the metric, and then there's scattering between different baryonic components and photons. And that's pretty much it. So you can evolve this through time with the Boltzmann equation plus linearized GR. You can write down some equations and then solve them. And you can get a CMB power spectrum out at the end of the day, or a matter power spectrum, or some other observable, given some input parameters. And so I wrote this code sort of in the context of the cosmological conversation that's happening right now. We're sort of in this era of tension cosmology, where you're trying to say what models give you a different Hubble constant. So these are the interesting questions. So maybe you can try to get a lower Hubble constant, or a higher one rather, by coming up with some model like early dark energy, where you insert some field, you generate a bunch of energy. But even when you add 2 parameters to your base model, somehow it's still difficult to fit all the observations right now. So this is a paper from Colin Hill showing that early dark energy messes up your matter power spectrum. So if you try to use galaxy measurements, for example, it basically prevents EDE from fixing your Hubble tension. And I find this kind of weird, right? Like, how hard is it to fit a curve with 9 parameters? I mean, you're giving yourself 2 additional degrees of freedom to fit 1 parameter, the Hubble constant. And I mean, early dark energy, there are ways to make it work, but it's sort of a very tuned model. I don't think as a physicist, you would say, oh, this is a very reasonable kind of thing to write down. Oh. So what is hard about this? Why are theorists not coming up with all sorts of crazy, great models to describe 1 parameter changing? And I'd say it's because we're in this era where the lambda CDM model has been so successful that codes have sort of hyper optimized for it. So for example, I'm a practitioner for CMB, for example, where sampling is very fast if you know the answer. So most CMB cosmologists just use Metropolis Hastings to sample. And in that case, or samplers like Metropolis, they have n² hyperparameters that correspond to a proposal density. And if that density is if it's very similar to your posterior, then Metropolis is fast. And if you get this proposal wrong, it can be orders of magnitude slower. So that means that if you already know the answer, then your MCMC chain will converge very fast, and you're happy, and you say, oh, lambda CDM confirmed. And if you don't know the answer, if you go a little bit off the path well traveled, it's taking a lot longer for you to get inference. And theory is also optimized for lambda CDM. So what's happening in Kam and class? So for example, in the early universe, there's this kind of stiff dynamics where the photons and the baryons are coupled very tightly. That's very bad for numericists because suddenly the time scale where the photons and the baryons interact is very short. But the time scale you care about is the Hubble time, the whole evolution of the whole universe. So it's very hard to compute. And so this problem has been in the field since Peebles in the 70s. Or the 80s, I guess, I'm not sure. Okay, but there's ways to get around it. There's this time-tested strategy where you write down analytically what's happening to the photons and baryons, and you can resolve it with just, now you can evolve your equations with just a regular Runge-Kutta ODE integrator. But you had to come up with this whole TCA approximation. And similarly, when you're evolving radiation-like components of the universe, they're not closed like the matter is in terms of these hierarchies. What that means is that when you expanded your equations, you get an infinite sequence of ODEs. So it's not very fun to solve. So you have to close it somehow, and that boundary condition that you used will mess up your answer if you don't get it right. And so what Kam and class do is something called the radiation streaming approximation. It fixes the problems associated with truncating your photon hierarchy or your neutrino hierarchy by evolving only the mean behavior and not the oscillations. And this makes modern Boltzmann codes fast. I mean, Kam and class are just amazing feats of engineering. And what happens if you don't want to do these things? What if you want to change the model? Suddenly your code is going to be 10 times slower or 100 times slower. Or even not integrable at all. If you don't, without tight coupling, a Runge-Kutta code has, I would say, no chance of integrating the photons and baryons. So the key, I guess, feature of Bolt is to leverage automatic differentiation. This is basically compiler-based chain rule. If you have some function that's defined by code, f of x, then the compiler can tell you the gradient of that function with respect to some other parameters that you care about. And so you get gradients of your observables. So here is some output from Bolt. This is the CMB power spectrum, and that's the gradient of the CMB power spectrum with respect to the baryon density. And this is the matter power spectrum, and similarly, you have the derivative basically of that observable with respect to some input parameter. And you get this, it's in particular, AD gives you exact, so numerically exact gradients. So these are very robust. And that lets you use them in things like sampling. But also, it lets you use implicit ODE solvers. In this case, there, now, I would say CAM especially is using numerical techniques from the 80s, 90s to really quickly evolve these equations. But over time, people have come up to deal with stiff ODEs. In particular, you can phrase it in such a way that you can integrate away the short time scale, the bad stuff that's happening between the photons and baryons, with some nonlinear solves inside. But to do that, you need the Jacobian of your problem. So this is the gradient of essentially the right-hand side of your ODE system. And having Jacobians calculated with automatic differentiation really lets you speed up this solution of this ODE and lets you solve stiff problems quickly. We also plan to incorporate this sort of recent innovations by Kamionkowski for integrating the Boltzmann equations without a hierarchy by rephrasing it in terms of integral equation. And that gets rid of this kind of radiation streaming approximation that's required in CAM in class. And the whole goal of this is that I want there to be a code where it's not way faster to do lambda CDM. I want a general code where you can explore the full the whole space of theories rather, and sort of sample through that instead of one parameter extensions to lambda CDM. And of course, having the gradient of your observables lets you speed up sampling. So it's long been known that strategies like Hamiltonian Monte Carlo, or I mean, recent implementations like no U-turn samplers, they can generate orders of magnitude more effective samples than things like Metropolis, because their autocorrelation is much less. So what that means is that sampling is way faster and more robust. You no longer need to know the answer in order to quickly converge. So this is all work done with a great team of people. Jamie Sullivan is a grad student at Berkeley. Marius Malaya is a scientist at BCCP, also at Berkeley. And the progress here is that we have a working Boltzmann code. It agrees with CAM in class to 0.1% in all the transfer functions and also observables. So it's now cosmology grade, and we can get gradients from it. So the next task is to tune it up in terms of numerical speed. But we also have plans to make it work on GPUs. So our task is now larger, right? We want to evolve, we want to carry around all these gradients of our observables with respect to parameters. So now GPUs are a way to do a lot of calculations in parallel. So they're better suited to our problem where we want the gradients of everything than they are to the old problem of computing just the transfer functions, which admittedly, I don't think GPUs would speed up class very much, for example. But again, like we're dealing with this more annoying problem of computing gradients. And so, these perturbations came from a GPU.
Zack,
Yeah.
Could I get you to expand a bit on the nature of the gradient to a straightforward gradient, which is you expect cosmological parameters, but you could imagine a totally different set of gradients. So what gradients are you explicitly talking about to speed up the two sides of Boltzmann equation, and what gets stored?
That's a great question. Yeah. So there were indeed two gradients there. Dick is quite perceptive here. There is one gradient here that corresponds to the equations themselves. That is the dependence of, so when you're evolving an ODE, typically you might have a left-hand side, which is the derivative of the state, and the right-hand side, which corresponds to. And the gradient of your derivatives of the state with respect to the current state. So this basically describes like how your change in the photons is affected by different, aspects of the baryons, for example, right? It's basically some characterization of your problem. This goes into an ODE solver. An implicit solver needs this Jacobian. And so you can use automatic differentiation to obtain that. So for example, this figure I've shown here is a sparsity pattern.
Is off the second derivative, not first.
Exactly. So basically, you would use automatic differentiation on, U prime, the state vector, the change in your state vector. Yes. And so this particular use of AD, it is essentially going to characterize something about your problem when you're integrating it. Yes.
Is that right?
Exactly. Yeah. So these are the things that go into the ODE solver. Yes. At the end of the day, that involves. So maybe I can just write. We can also chat about this later. But so this matrix right here is that thing I'm describing. That is. So for example, the rate at which the photon perturbation is changing with respect to time, like that's something that goes into the ODE, right? And that thing depends on the current state, like the amplitudes of different things. So that is characterized by basically this matrix, the dependence of different parts of your state with respect to other parts of the state.
But you mentioned with respect to omega B, for example,
Yes.
that is outside the model that's being computed,
Yeah.
unless one's trying to build something to make a some kind of grid interpolation. So within the calculation itself, presumably it's not those gradients, it's other gradients.
Exactly. Yeah. I can. Yeah. We should talk about this later. But basically, there are two ways that ADs.
But are they basically time gradients?
One of them is the one in the ODE is a time gradient.
Yes.
The one in the okay. I would say neither is really a time gradient.
But you are working in case space, right? So
Let's chat about this later.
okay.
It's somewhat technical. Okay. Okay. So great. This code now is cosmologically it's ready for further elaborations. And I'm really excited about it. I think that this tool will let us explore the space of theories much faster than what we have right now. So just to summarize, I talked about, went all the way from data to perturbations here. The CMB experiments, they're going to continue to scale through this next decade with this final CMB S4 end goal. And there's a lot of guaranteed science here, things like neutrino mass or the number of light relics, a lot of astrophysics to learn as well. But also I'm hoping for a few surprises, things like the Hubble tension. When you increase precision a lot, you can often, the tide rolls back and you can see some new stuff, hopefully. And so to analyze all this data, we're going to need some nice simulations, things like WebSky. So we have this half-dome suite that we are targeting as sort of this instrumental simulation set. And we want to explore the space of theories in order to really give reason to take all this data. And I'm hoping that both will be one way to do that. All right, thank you so much.
So is there a question also from the Zoom or from the room? I see the hands raised from Ik Chen, so you can ask the question.
Oh no, that's a clapping hand.
Oh, right. Sorry. Sorry, the computer here was muted, so could you repeat the question once again?
Oh no, that's a clapping hand to thank Zack, our speaker.
Oh, sorry, I didn't. Okay. So any other question? Yeah.
Just a bit of a practical question in a sense. So what you're essentially trying to do is to say, okay, one calculation of your Boltzmann code, no matter which kind of model you want, should take a couple of seconds, or
Yeah, that's the target. Yeah.
And like with GPU parallelization, you really want to bring this down to exactly that level. And you're talking about single GPU.
Yes. Yes.
And whatever the sampling or the inversion of the problem is then taking like hundreds of seconds or
That's the dream. Yeah.
Okay.
No matter what the model is, right? So I had this slide. See this. Oops. You know, we're restricted in terms of the interactions in a typical Boltzmann solver, right? It's sort of this is really the sort of interactions you want, but I want to be exploring all possible interactions of components, or even arbitrary numbers of new components. I want to, yeah, open up the freedoms.
Do you give me a sense of like how many? So what are the problems? Do these codes exist and these extensions exist, but they're just slow, or do they not even exist? Or
oh yeah, so definitely a lot of effort over the years into what if we opened up an interaction in this sector, for example, or what if we did something like this, or what if we changed this interaction just a little bit. So those are all totally out there, and people have done great science to sort of analyze these. What I'm interested in is sort of inverting the question. I want to know things like, what are all possible solutions to the Hubble constant? What are, what are the allowed interactions that the data tells me? Right, to sort of more broadly sweep through, instead of just like these little hops away from this lambda CDM point. I want to be sweeping the whole region.
so this sounds almost like you're trying to figure out the PDEs from the data.
That's a great point. So yeah, later down the line, I would love to solve some PDEs. Yeah, I think there's also stuff to work on there. Right? So the universe we think is very linear, but doesn't have to be that way. There could have been things like black holes. We're pretty sure we're there, and those things are very nonlinear.
Yeah. This sounds really exciting.
Those things can be simulated via PDE, then packaged up in some surrogate or emulator. You can stick it back in this model. Yeah, I think that's a great idea.
This code publicly available?
It is on GitHub, but I wouldn't recommend you use it yet because we've been committing to the main branch pretty regularly with abandon, I would say. Yeah. But yeah, so it's sort of, we're still putting it together. Yeah. the interface very, very rough for now. But okay, so another reason, just to add, another reason I'm excited for this code is that I really dislike writing C code. You know, so as a grad student, I wrote a lot of C code. As an undergrad, I wrote a lot of C code. And I feel like I wanted to become a scientist to think about the universe. I don't want to think about pointers. And so, for example, so this code is written in Julia, just an implementation detail. It doesn't really matter, right? But this language does let you write very compact notation. So this is the evolution of the relativistic neutrinos. This is straight out of Mon Bertschinger, like these expressions. So you can, another reason why this code is nice is that you don't have to think about so many other things like bookkeeping.
I think it'll probably be good for us to be doing this over coffee, but for the neutrinos, like we do, and I have in my codes, it's L propagation with a damper at the end. And what we did is that basically the L hierarchy got abandoned because we went back to the integral formulation. And one of the very effective things, who would have thought it, spline safe today, as you know, except that when you start to go to different models, you have to put more and more meat into the splines, which is what the slowdown was. I assume you're still using the spline approach or not?
Yeah,
integral formulation.
Right. So there are a lot of splines in this code. We're still working on this integral formulation.
Yeah,
It's not.
Is that,
I think it's
settled called the radiation something or other thing, the radiation streaming approximation?
That's a totally different thing that Cam and class use. But yeah, it's a little bit like we could. This is, I think, a technical detail we can talk about. Yeah, over coffee. Yeah. So yeah, eventually we'll get to this integral approach. But it's not clear, I would say, what the best way to implement that numerically is. Yeah, Kamionkowski's paper is very light on the implementation.
But the integral approach goes back.
Oh yeah, absolutely. Yeah, we should chat about that. Yeah, I'm eager to hear what you have to say.
Is there any further question? I don't see any question on the Zoom. Yeah, if there's no question, then let's thank the speaker again.